Welcome everybody for this session. So I will talk about the integration of III-V RFICs component in antenna in package module in PCB-based embedding technology for 5G and 6G applications. We observed the last 10-20 years increasing the increase of the operating frequencies of the different systems. Mainly because of the high demand for data rates, low power consumptions, and also to reduce the latency on the different telecommunication systems. We saw already that for the 5G products that it already goes above the 10 gigahertz, but also reaching then 40 gigahertz bands. And also for the 6G applications, the operating frequency will be above 100 gigahertz. So the main challenge, if we go higher on frequency for millimeter wave and sub-THz systems, is that with the same system, with the same design techniques, then we observe some decrease of output powers. And then the efficiency of the whole system is also decreasing. Usually we use CMOS silicon-based technology. We use this technology because it's easier for the integration, also for cost-wise. The clean room are really developed with this technology. That's why then the costs are usually reduced. But in parallel of that, there's a lot of studies on III-V components, III-V semiconductors with indium phosphide, for example, the transistor, the HBT or the HEMT, or also on gallium nitride, but also on silicon, the germanium. But yeah, these technology are really developed because it's presents some really good properties with higher mobility. The charge density is also higher, and also present also some really good breakdown voltage. But what it interests us, it's here, for example, we can see that I showed here the saturate output powers of power amplifier versus the frequency, and depending on different technology. And you can see that for CMOS technology, then we have some pretty good results. But if we use different III-V technology, for example, the GaN technology, then we have higher power levels, and it's really preferred technology if the operating frequency is below 100 gigahertz. But the indium phosphide is preferably used when the operating frequency is above 100 gigahertz until 300 gigahertz. The problem by using this technology, by using these substrates, is that it's pretty costly substrate, and then it's make the whole system, if we want to develop it with this III-V material, then it will be a really expensive system. So that's why the idea, which was also decided with different companies and with the different research institutes, is that instead of making the whole system within one material, is really just targeting specific functions like power amplifiers, the different functions which required a lot of powers with these III-V materials. And then we can see here that there's a need of combining then the CMOS, standard CMOS technology and the III-V technology. And that's why then there's a need of heterogeneous integration. So here, what is then the problem for integrating the III-V components? And it's usually first because of the back-end of line of this technology is made of gold, and the gold, and if you want to make some standard integration like with flip chip, then it's already quite tricky. But with this back-end of line, then the top layers of gold is really thin. It's around 3-5 micrometer, which make a standard integration quite tricky. The second problem is the presence of air bridges. Since the backend of line, it doesn't have a lot of metallization layers, then usually this component, these circuits have a lot of air bridges, and the problem is that if we press it, if we really want to use it on integration, and if there's a little bit of pressure on it, then the air bridges can be damaged, and then the whole circuit will not be functional anymore. And the most problematic of this circuits is the thermal management. Like I mentioned already, that this material can dissipate a really high power, then the heat dissipation of this circuit is really critical. Then for the integration on the packaging, then it has to be really well considered to make sure that the heat can dissipate out of the packaging quite smoothly. So I'm talking about the embedding process, but here I will just show you this overlook. How does it work? Then first we have the substrate, the PCB-based substrate. We can attach the chip directly with a sinter glue here. Make sure it's here, and then make some cavity on the pre-preg layers, and then directly then connect on having some different thin film layers, and then drilling it, and then plating and structuring the whole interconnections. So what's the implication of this technology on RF? What is really critical for RF when you go really high on frequencies, the impedance. And you can see that at the beginning, for the traditional concept for integrating the ICs to the packaging, we used to have some wire bonds. This has a impedance, inductance around 10-20 nanohenry, which is already quite high, especially if you go on a really high frequency. And then there was the technology where we put the chip into a cavity, and then having the wire bond, then we can reduce the length, and we have a straighter connections between the component and the packaging, which then reduce the inductance of these connections to 100 nanohenry. And then there's some research done on the wire bond itself, and instead of having a wire bond, using some rubber bond, and this can reduce the inductance to 5 nanohenry. And since 2018, then in our institute, then by using this technology, the embedding process that I just mentioned, then we could characterize the connections that we have from the IC out to have an inductance lower than 1 nanohenry. So that's why this technology is preferred for high frequency applications for us. How can we use this technology for 5G and 6G applications? Is to use this for antenna in package configurations, where we have the different ICs within the package. Below the different ICs having the heat dissipations to make sure that the heat could be then cooled down in the system board. Placing some decoupling capacitor if needed within the package, and then routing out above for the antenna if we have some transmissions, and also having the possibility to route it down to the system board, where we can have all the power supplies and the digital control here. For the demonstrator for these presentations, then we have here a beamformer IC made in silicon germanium technology here in the middle, and then having the power amplifier and the low noise amplifier on GaN technology, gallium nitride technology, separately having the connections between the beamforming IC and these power amplifier ICs, and then having from the amplifier IC the routing to the antenna. So here I summarize a little bit the challenge before I can describe you the technology process that we have for this technology. So if we go into a standard embedding process where we embed some standard IC, then we have usually some 10 micrometer thickness copper on pads. And for this work, then, like I mentioned, these 3-5 components where the top layers have some gold pads of 3 micrometer. So this is one big challenge. Also on the power dissipations, when we have some power electronics, is around 0.8 watt per milli square meter on power electronics, and on this work we have 1.5 watt per millimeter square meter. And also the IC have some air bridges, which make then the integrations a bit more tricky because any air pressure can destroy the air bridges. So we have to make sure that the air bridges will be well preserved after the embedding process. So our initial approach in Fraunhofer IZM is to use some thin film material, some thin film directly above the dies, so then we can process and make sure that the drilling will not go through the pads. So here I can show you the different steps. So like I mentioned, first we have the die placement, then the embedding process, laser drilling, sputtering process, and electroplating. So first on the die placement with the sinter glue, we used the sinter glue from Namix. I have the parameters here, but I will not go into the details, but we tested different sinter glue, but this one from Namix was having some really good performances also on the thermal conductivity. And when we make the shear test, but also with the X-ray inspection, then we didn't observe any problem also on the flatness of on the IC afterwards. In the embedding process, then we have first RF material, the pre-preg material on the Mectron 7N. We make the cavity, and then we go with this material we place it on the 3-5 components, which are already then placed on this layer. And then on top of it, then we have the thin film material where we can make, we have the standard lamination process. And on the laser drilling, then you can see that we go here, and then the ICs pads are here. Then we see that we don't destroy the pads, and we have then the connections here. And then when we're here is the cross sections of after the laser drilling, and you can see that here we can drill until the gold pad without damaging the 3-5 material below. And so now with this, of course, it was for us an explorative study to make sure that we can find the appropriate laser parameter to make sure that we are not destroying this the contact pads. But then we use the FIB cut to make sure that everything is fine and that we are not destroying anything on the IC. So we are showing here that it's possible to stop at a 3 micrometer gold path. And after this, then it's a standard sputtering process and electroplating. So I will not go into the details here. Here is on the vias. So I showed you then the laser drilling cut here just previously, and here you can see after the plating process that there's a good connections, and of course we also check it electrically so that the connections is really done here. And then what is happening on the air bridges? It's something that I mentioned that is a big challenge. I don't know if you can see here between here and this white connection here is one air bridges, and here it's after the embedding process. So what is in gray here and here and here is this thin film material. That when we apply the thin film material, maybe I can go back here. Yeah, when we apply here the thin film material, for a short moment of time when we're applying it, it becomes a bit liquid. And once it becomes a bit, it's not really liquid, but a bit more, it can go through the different holes, and that's why then it goes through the air, below the air bridges, and then filling the air bridges with this thin film material. And that's why then after embedding the components, the air bridges are not damaged, because it's filled with this thin film material. And one big challenge also on the thermal management, then we made some simulations to see how we could take the heat generated by the ICs out to the system board, and we make the simulations either with thermal vias, some silver sinter, or some core copper core. So we made some different simulations to see which material and which topology will be the best for taking out the heat dissipated. And the best compromise that we found was with this thermal vias because of the density on the manufacturing process. So once we use this technology to embed the different IC, one big challenge is also to simulate and to design the whole antenna in package module to make sure that all the different interconnects have the proper characteristics for transmitting the different RF signals. So we use ANSYS software, HFSS, to simulate each interconnect, of course, the interconnect of interest, where the RF signals are impacted until the antenna. And also the antenna are simulated with HFSS. One example here is that we have the transmission line here, and then we have some interconnects going down, and then having some different lines. And then we also realize this structure, this interconnect, to compare the simulations and the results. You can see here that we have some good matching between the simulations and the measurements on the insertion loss, but also on the return loss, and we are doing it for each interconnect present in the module. For example, here from the ICs to the system board, there's sometimes the clock required to be fed by the system board, of course at lower frequency, but still on RF. So that's why then this connection is quite critical for us. And that's why then we have to make these simulations from this interconnect, and then seeing if how many vias and for how many layers to make sure that we have the best transmissions from one point to another. Yeah, and here we have then the insertion loss, but also the return loss results for this interconnect. Then I'm showing also here the results from the ICs, the full signal bus from the ICs to the antenna. Then you have here the simulations. Of course, here I shows with different vias going through the different material, but then we can also split them to easier to make sure that we understand from each layers the different performances. And then at the end, if we understand the full path, then we can make the full path simulations between this here, between the IC itself and then the antenna thing. Then for the antenna itself, then here I'm showing you one antenna which was used for the 5G applications. Then it was at 39 gigahertz, so you can see that the bandwidth is around 3 gigahertz, between 37.5 gigahertz to 40.5 gigahertz, and then the measurements is matching quite well the simulated results. And also on the peak measurements, then on the peak gain from the antenna, then we have pretty good matching between the simulations and measurements. Here is for the antenna array, a single antenna array, but then yeah, we did it with different elements also if we want a full array. And for each small structure, then we have the different simulations and the matching structure to compare with the measurements. Here I show you then the full module that we manufacture. The total size is 9.5 millimeter by 15 millimeters. So you can see that here are the antenna array that I show you, where we make the elements, single element characterizations, but then we place it to have a 2x4 antenna arrays. So this package has 6 metal layers and around 2,700 microvias. So you can see here actually the different microvias. So on the different process step, then it goes more than 130 process steps, because we have 6 layers, and then on each layers there's a lot of vias, there's a lot of process step to make sure that the whole module is working properly. And below, on the bottom face of this module, you can see that here we have a LGA layer, and directly below the ICs, then we have a copper plane to make sure that the heat dissipations can be taken well after this. Then we place this embedded antenna in package module on a PCB board to test it. So we have the power supplies and also the digital control of the beamformer ICs. And then we have also the RF feeds for the clock and the pin headers for the digital control here. We have a setup where we could have use this module to make sure that it could then work, and then we have an antenna to check then the signal which is provided by the module, and then we can see here that the beam angle it's matching pretty well from what we measured and what we calculated in advance. So here is a pretty good matching between the two. As a conclusion, can say that here since 2018, when we started this embedded process for RF applications, we managed to show some different demonstrator which could then prove that this concept could work. The first project was the Serena project, which also then bring different projects because we could see that there's a different interest from companies and from partners who see the potential on this technology. The 6G Sentinel, TICOS, and 6G Teracom project are German-funded project. 6G Sentinel and TICOS ended already, but this 6G Teracom started last year, is still running. And we see the interest of this technology because next year, January, a new EU project will start, Extreme 6G. So it's about telecommunications project on the D band, so 140 gigahertz, 140 gigahertz, and using this technology. So we could see that there's a big interest from the partners and from the industry on this technology. So with this, my talk is finished. I would like to thank you all, and I'm open for questions.